असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्युर्मा अमृतं गमय। वन्दे मातरम् वन्दे मातरम् सुजला सुफला मलयज शीतला सस्यश्यामला मातरं वन्दे मातरम् शुभ्रज्योत्स्ना पुलकितयामिनी भुल्लकुसुमित द्रुमदलशोभिनी सुहासिनी सुमधुरभाषिणी सुखदां वरदां मातरं वन्दे मातरम् वन्दे मातरम्।
Hello everyone. Happy Independence Day to one and all. It's my great pleasure to be here. So we are here in this wonderful event, Math Ecstasy, an online Odyssey through mathematics, national webinar series organized by Math Aspirants team. So today we have its 9th national webinar, Beauty in Mathematics, and we have our wonderful speaker, Professor B. Sury here. So let me talk about Math Aspirants a little bit. So I've been associated with Math Aspirants for a long time. We had our very first national webinar on an Independence Day in 2020, which is 3 years ago. And now we are having its 9th national webinar on another Independence Day in 2023. It's such a great pleasure, and we are feeling so proud. And it's not happened in one day. We got our pillar, Dr. Vinod Kumar Sir, Associate Professor, TMG College, Tirur, Kerala. Everybody in this meeting definitely knows Vinod Kumar Sir. So he has been working so hard to build this big community. It was started as a WhatsApp group, and now it is having members from even outside India. So it's got so much bigger. And I would like to mention each and every member of Maths Aspirants at this moment, because every person has contributed something to this. Not only teachers, not only students. It's about saying like big. It's everyone who wished well for this community to become big. So everybody here is also a part of this success. So it's our celebration time when we meet like this in a large scale. And I would like to mention Dr. Bijumon Sir too. He was like a backbone for this team. He did all the technical backgrounds and YouTube publishing that we found very helpful for the new audience. So it's like a big teamwork. Vinod Kumar Sir, especially, I would like to tell a few things about him. He is always so inspiring to each and everyone here. Even you are a new person in this group or an old person in this group, he always find his time to motivate, to inspire, and to reflect our talent, which could be beneficial for this community to grow. So this community is a big platform now, which discuss problems and celebrate maths events, and every math lover find this community charming and really having a future in future. So and also I would like to mention Dr. Kumar R, Emeritus Professor of CUSAT. He was like a guiding light for every event, Maths Aspirants coordinator. His guidance and advices were really a big thing for Maths Aspirants. So we are really honored with Vijay Kumar sir's presence here today. And also there are a lot of teachers which I didn't say by name, but really a motivating factor for all the success we had so far. And our chief guest, Professor Dr. Sury, he is from Indian Statistical Institute. We are truly honored for you to be here, sir. It's our great pleasure to listen to your talk today on our Independence Day. We are so happy and totally excited to hear from you. Okay, so with that, I would like to welcome all of you to today's event. Each and every person here is so important, and I'm truly happy for you to be here. Now, I would like to welcome Dr. Vinod Kumar sir to share a few words with us.
Dear friends, Independence Day greeting to all of you. I feel very proud to welcome all of you to the 9th National Webinar in the Math Ecstasy webinar series organized by our Maths Aspirants groups. Today, we are all blessed to have Professor B. Sury of Indian Statistical Institute, Bangalore, to have a invited talk on the topic Beauty in Mathematics. I would like to express my sincere gratitude and thanks for accepting our invitation and joining with us. I would like to thank Professor Ambat Vijay Kumar sir for helping me to get connected with Sury sir. I would like to thank all the members of the organizing team and supporters of Maths Aspirants groups. I'm sure that the coming hour will be certainly a great academic feast for all the members. I welcome everyone to this event. Thank you. Jai Hind.
Now, I would like to welcome Dr. Vijay Kumar Ambat sir, Emeritus Professor of CUSAT. He would be giving a nice introduction for our chief guests today. So welcome, sir.
I'm extremely happy to introduce Professor Balasubramaniam Sury, who had his BSc Honours from Hansraj College, Delhi University, and MSc Mathematics at Indian Institute of Technology, Delhi, and PhD from Tata Institute of Fundamental Research under the guidance of Padma Bhushan M.S. Raghunathan, FRS, a renowned mathematician of the country. He has been in Indian Statistical Institute as a professor since 1999, and he is an elected fellow of the National Academy of Sciences, and he has been the national coordinator for the Mathematics Olympiad program in India, and also served as the president of the Indian Mathematical Society in the year 2020. He is also the chief editor of the science education magazine Resonance, published by Indian Academy of Sciences. He is also an author of a couple of books, Group Theory by University Press, Number Theory and Combinatorics by Indian Academy of Sciences 2017, and also a co-editor of the Indian Statistical Institute series of publication on Leavitt path algebras, jointly with my colleague Dr. Ambuli, who is incidentally the doctoral student of Professor Sury, and Roosbeh Hasrat, which was published in 2020. As I told you, above all, we have been friends since 1981, when we met at a workshop organized by Pune University in 1981. Another member of that workshop, Professor Ramaswamy from University of Mysore, is also with us. So welcome you all once again, and congratulate the Math Ecstasy group led by Dr. Vinod Kumar, Dr. Bijumon, and supported by very many research scholars and master students from all over India. This has been a successful program since many years, and I wish you all the very best, and thank you very much.
Thank you so much, Vijay Kumar sir. Your words were really a blessing for today's event.
Happy to welcome Balasubramaniam also. Hello, sir.
Thank you.
Hello, sir.
It's so happy to see you all here, teachers and everybody. So if you would like to give a huge clap to this event, you are all welcome to type greetings in the chat box because we know it's an online Google Meet and we cannot see each other, but everyone is so important here. So yeah, that's great to see, and it would be like a great motivation and cheer up for everybody here. So thank you so much, guys. You are so lovely. Now, the mic is over to our chief guest, Professor Dr. Sury. Please welcome, sir.
Thank you so much. It's first of all a great pleasure to be here, and I wish everyone here a very happy Independence Day. And I must thank Professor Vinod Kumar and his team of Math Aspirants. Really, it's a great effort. It's a great initiative, I would say. It's been going on for a few years, and we can see the response. I was told that I sent a list of people who registered, some 1,000 odd people registered apparently. So that itself shows the popularity of this program. In general, I would like to speak in person. I would like to meet people and speak in person, as most of us would like to. But there is also a blessing in speaking online because many more people from different parts can join. Nevertheless, most of the time it looks like you're conversing with the computer. But I hope that at the end of the talk, at least, or if not, even in the middle stages, people can perhaps raise questions. And looking at the kind of diverse audience, I decided that I'll choose a topic called beauty in mathematics. Okay, so it's a bit of a people can wonder what I mean by that. I'll make it clear soon, so that most people can perhaps relate with it in some way or other. I'll start by sharing this file. So I would start. This is the title I have given here. Beauty is truth. This is because of the following two lines of key. In this ode on a Grecian urn, the urn is supposed to speak, and this says the following: beauty is truth, truth beauty. That is all you know on earth, and all you need to know. So I like these lines a lot. So what do other people say about beauty? Hardy, for example, said that mathematicians' patterns, like the painters or the poets, must be beautiful. We got muted,
Sorry.
but
Yeah.
Now you can hear me, right?
Yeah.
Yes, sir.
Okay.
Okay. So let me come back to the file now. Always finding the file is a bit of an issue. I'll make it full screen. Okay then. So as I was saying, just quoting G.H. Hardy, the great G.H. Hardy, whom all of you know by name. So there is no permanent place in the world for ugly mathematics. That was his quote. And in this same vein, several people have expressed sentiments. People like von Neumann, Poincaré, Hermann Weyl. For example, Hermann Weyl goes a step further and he says, although in mathematics he looks for truth and beauty, when he has to make a choice, he chooses the latter. That's a very strong statement. And in this context, I would mention Paul Ehrlich, the great mathematician, wandering mathematician, one might say. He referred to something called the book, in which God keeps the most elegant proof of each mathematical theorem. In 1985, he had said, you don't have to believe in God, but you should believe in the book. Okay, so about 25 years ago, such a book was published called Proof from the Book. I think most people will know about this book. This is dedicated to heritage, and so many theorems which we know about, very beautiful proof, sometimes multiple proof. So of course, when we talk about beauty, we would have to agree that this is a subjective thing to say. No? Some people, it is all in the eye of the beholder, as I say. Beauty is in the eye of the beholder. But when I see beauty, it will also be seeing with the mind's eye. As you can see, we can just see with the mind's eye. Poincaré, again, as we know, who discovered lots of topology and geometry. He was blind, and Beethoven was deaf after a little while. So this seeing or hearing can be more abstract. Anyway, so though it is subjective, I will nevertheless try to speak of something which I feel are beautiful. And when we say talk about beauty, first of all, we should also think about whether it is important to look for beauty at all. Notwithstanding what Hardy said, we have this quote by Kepler. Kepler says, this is his quote, this is something that he did in the earlier stages. A famous demonstration of looking for beauty involves the appearance of a Platonic solid, the early work of Kepler. So he had proposed a model of the solar system. This was based on the distances between planetary orbits and looking at the 5 Platonic solids. It was a very beautiful idea, but it was doomed to fail because it was not correct. He himself rejected this idea model, and instead, so for him it seemed a definite step backward. He rejected it, and he said this discovery he compared to a wagon full of manure left in the Augean stables of science. So it's sometimes it's debatable whether you would go for beauty or not. Anyway, so I will now. I just want to, before I start, I want to warn people that if you think that by beauty, what I'm going to talk about is something like this, showing pictures of this. This is a Renaissance period when Leonardo da Vinci and others, for example. This is the so-called golden ratio and so on. People talk about the golden ratio as a mark of beauty. And or if I talk about this so-called crystallographic group, there are 17 such groups here, and all of them are in this picture. You can see there are all 17 are represented actually. This is from Alhambra in Spain. Or if you think I'm going to talk about this, this is a so-called this is actual crystal actually in nature, which occurred in nature, and it reflects this aperiodic phenomenon. It was predicted by someone who got the Fields Medal. Sorry, I should say Nobel Prize because it's chemist. And such things occur in nature. They are beautiful. Of course, you would have seen also pictures by Escher, like this. This is angels and devils. This is the angels devils on the so-called Poincare disk. In fact, by the way, Escher had visited Alhambra several times. Or this, of course, a lot of people are fond of looking at this Julia sets and this Mandelbrot sets and so on. I don't mean by beauty these things, because in some sense, these are kind of just on the surface, really visually pleasing, but some of them may not have deep mathematics. So what would I consider as beautiful? So in this context, I just want to mention first, about 35 years ago, the mathematical intelligencer had run a kind of a voting procedure where they had asked people to vote on some number of problems, which are results which they thought people could vote for in terms of beauty, rate them and so on. So I'm not going to recall all of them. There is no point. You can look at the intelligencer volume for what the public mentioned, but I do mention some of them and some others which I feel are beautiful. Of course, in terms of beauty, some of them are also easy to prove, some of them are difficult to prove. So it has of varying difficulties. Also, sometimes the result looks very interesting, the statement that is, but proof may not be that interesting. Whereas sometimes the result, the statement itself is not that interesting, and we know the proof is beautiful, what we call as beautiful. So there is a lot of people would agree on some proof being beautiful if it is very elegant. But what I would think of as beautiful in some sense, if I want to pinpoint one aspect, is that there is an amount of surprise. Some disconnected things seem to be connected. That would be one thing. Or a very simple looking statement giving rise to very unexpected application. So let's go further now. So as I said, it's a particular proof which could be beautiful. So let's start with some of the results. I'm going to talk about some around 15 of them. Okay, so some of these are included in the intelligencer, but some of them are not. So I hope people can enjoy. Let's see. As I said, my conclusion is that it has an element of surprise. Whatever you might agree is beautiful, all of us might agree as beautiful, would have a common element, which is that of surprise. Let's see if you agree. So let's hope it is effective as well as inspiring for math aspirants. So what I will do is, when I look at some of the results, I might branch off a little bit and talk a little bit more about the results and some applications, not just about the results. The first is the so-called Euler's formula, V minus V plus F equal to 2, because most people know about this, and many people also know how to prove it. This is course, discovered by the great Euler, who was the most prolific of all mathematicians. So we also know that apart from such a beautiful formula, it is also very, very useful. Many diverse situations can be applied. I'll just mention a few. So of course, we know that this concept has been generalized. It's called Euler characteristic in this context. And so, for example, one immediate application of Euler's formula. I wanted to mention this application because some people don't seem to be aware of this, not very well known. When we in school or college, when we draw the Venn diagram, people draw circles, intersections of sets that depict as circles. So I would think that if there are n sets and you want to depict all the intersections, so there will be 2 power n intersections, but through circles you cannot depict it, all the 2 power n. For example, if you take 4 circles, number of regions that it produces are the most 16, the most 14 actually. What we want is 16. I have not drawn it here, but you can draw and see that it can produce at the most 14. So this fact that it cannot produce all the 2 power n, or it actually produces these many regions, is an application of Euler's formula. But of course, what does one do then? You want to depict in terms of Venn diagram. So I'll just flash one picture. For Venn diagrams, don't have to be circles. You can draw other kind of curves, Jordan curves and so on. So I'll just mention one for the cases n equal to 5 and n equal to 7, 5 sets and 7 sets. We need the curves for that we have 2 power 5 regions. In this n equal to 7 case, you need 2 to the power 7, which is 128 regions. Here are some pictures. You can have different shapes. So people may not everybody may be aware of this fact that Venn diagrams cannot be drawn only with circles. Just enjoy that many more one can do. But I just touch upon this and go to one other application for Euler's formula, which is also very well known, sixth theorem. We have a closed polygon and whose vertices are lattice points. Then you can count the area by looking at the number of lattice points inside and on the boundary. And this is a well-known formula called Fick's formula. And this is an immediate consequence of, or very quick consequence of Euler's formula. And in fact, you can go further, more that Fick's theorem can reveal. For example, if a convex polygon with lattice points as vertices contains I points in the interior and B in the boundary, you have this kind of inequality. This is shown much later in the 90s by Peter Scott. This is an elementary proof, but using this, what he did was, so first let's call a polygon to be legal, a polygon which has exactly one lattice point in it. So let's move it so that it is just 0, 0. And what he found is that there are very few legal polygons. Namely, they are exactly these 16. They call it 16. Okay, now around the year 2000, I think, using the theory of modular forms, this is one of the higher theories, some higher mathematics, so to say, one can prove something. So look at these 16 pictures. So here is something, as I said, it requires some slightly higher level mathematics. I'll just mention it in passing. Suppose you can understand some of this with a picture. If P is any legal polygon, that is a polygon with exactly one lattice point in the interior, suppose the vertices are P1, P2, Pn, you define a dual polygon, P hat. Okay, the smallest convex set which is containing the following points: P2 minus P1, P3 minus P2, these endpoints, some of them can coincide. Think of these points as vectors, and Q1, Q2, Qn may not be distinct. Okay? So for example, let's see, look at the picture. Here is the polygon and its dual. Okay, so P2 minus P1 is Q1. Let's think of this as origin. P2 minus P1 is Q1, etc. So as you can see, Q3 and Q4 coincide. So for this polygon, the dual polygon is this. What happens is, remarkable fact appears, which is that if you look at so-called discrete version of length of this boundary segment, which means just count the number of lattice points on the boundary. So this number turns out to be, for the polygon and its dual you add, turns out to be 12 always, for all the 16. This is true for any of these legal polygons. So I just want to say that this is related to Ramanujan's first form of weight 12, so called Ramanujan form. only equals form of weight 12. So that is a 12 here. Okay, so I think enough of this application. We'll go to, okay, one more application of Euler's formula I want to give. This is the fact that there are exactly 5 platonic solids. Okay. So how do we get that? What is a platonic solid? Okay, this is the description is given here. The faces meeting at a vertex are regular polygon, and all of them have the same number of sides, and then number of faces meeting at each vertex is also the same. So this is a this is called a platonic solid. Suppose there are V vertices, E edges, and F faces in the solid, and the faces on the regular polygons with 3 sides. Let us count the edges by counting the faces. You can count the edges by counting faces. Next time we can count it in a different way. Suppose we get P times F edges, but you see we have counted each edge twice as it is the edge of 2 connected faces, 2 faces that edge as a boundary. So we have counted it twice. So we have 2 times each here. We have 1 such. Similarly, counting the edges by means of 2 endpoint vertices. Now we are counting vertices. Q is the number of faces meeting at any vertex. Okay, this Q is the same. So Q times V, we are counting, is also the same as 2 times V, because we are just counting the edges twice. So this formula immediately do some little algebra. You can rewrite it like this: V by this, E by this, F by this. Now you know what to do, because V minus E plus F is 2. That is Euler's formula. To use that, you get this following. Just put V minus E plus F, get this number, which means it is being hidden a little bit. You can rework it here. You can just rework it, and then you find that you have this number. So because of this number in denominator, 4 minus P minus 2Q minus 2, you know that P minus 2 times P minus 2 is at the most 4. This being positive. So you can just work out all the possibilities. These are the only possible. And they give the 5 solids. Tetrahedron in this order. Octahedron, icosahedron, cube, and dodecahedron. So this is a very nice application of Euler's theorem. So let's go to the second. So you would agree that Euler's formula is beautiful and also is very useful. In your voting, I don't know where it will stand, but nevertheless, in most people's voting, it stands quite high. So let's go to the next example. So this is may appeal to some people, may not appeal so much. This is also called Cayley-Hamilton theorem. Whenever you have a matrix, a square matrix, then if you fill the corresponding characteristic polynomial, it's the root of this characteristic polynomial. Incidentally, this result was mentioned in the mathematical intelligence voting. I myself voted it one of the lowest, but some people might like it higher. In any case, so I would in fact mention the kind of proof that I would like to think of. Many people, when they first look at this, they might think, oh, we can just put C equal to A and it gets 0. So what is wrong with this proof? You must think about that. Okay, so why is it not an obvious statement? So, but one can always work out a kind of proof where you look for a candidate and find it. You look for a candidate, what it should satisfy, and then find it. So this is easy to do. I just gloss over it here. I mentioned it here. So you can look for a candidate. The main thing that you want to use is this formula. That is, a matrix times its adjoint is the characteristic polynomial times current. A minus Ti is this matrix, adjoint of that is. So using this formula, you can work out coefficients of powers of T, and you can get this kind of relation. AA0 is this. So you can, from that you can work out that this is actually 0. This matrix P of A is a 0 matrix. In fact, I would just leave one more little fact for people to check who have not seen this. The same proof is actually, the above proof gives the following more general result. If 2 matrices commute and look at the characteristic polynomial of A, which is your P of A is 0, P of B will be B minus A times C for some matrix. Okay, this is very interesting. Okay, this is a minor application, I would say. Then I'll go to the next example. Okay, so this again, in fact, I would have liked to spend a lot of time on this. Some other talks I have done so, but I would, and I think I will get lost in this. There is so much in this. Nevertheless, it's for so beautiful Ramanujan formula. This is the so-called partition function. P of something means number of ways of partitioning that number into smaller numbers. Right? So P of 5n plus 4. So you want to know something about these numbers. So look at the generating function. The generating function satisfies this very beautiful relation. There is a product, infinite product here, divided by another infinite product. So these kind of things, generating formulae, give you a lot of congruences. That is, number of partitions of 5n plus 4 is a multiple of 5 and many such. Okay, now this theory is built up a lot. Littlewood refers to this formula as a formula of supreme beauty, because Hardy himself calls this an example of Ramanujan's best work, whereas some other people would consider some other things like this work on such form, Ramanujan's modular form, as his best work. Nevertheless, it's just debatable what is this. It's really beautiful, nevertheless. And this, I said, it gives an enormous impetus to the subjects of modern subjects of elliptic curve and modular. These are central themes in number theory. When you prove things like Fermat's last theorem, these are involved in it. These are the principal characters. So another result about in passing I'll mention, this is again very beautiful. Number of partitions of a number n into odd numbers is also a number of partitions of n into distinct numbers. Somehow these two match. And the proof of this is also using generating function. Okay? It is not something visible. I'll give you one visible example. So what I mean by visible is I can give a actually geometric or bijective bijection between the two numbers. Number of partitions of n into at the most m parts equals the number of partitions of n into parts in which each part is at the most m. Okay, number of partitions into most m parts is also number of partitions in which each part is size at the most m. So you can imagine, you can draw a picture. I mentioned, I don't have picture here, I think. So let me just mention it. For a partition, suppose I write the partition as n1 plus n2 plus nr, where n1 less than equal to n2, so they can repeat, right? 1 plus 1 plus 1, it could be like that. Draw an array consisting of dots with n1 dots in the first row, n2 dots in the second row, etc. Second, sort of center to the left. You have a picture here, and then the picture, you read it, row and column you interchange. Then you'll get a so-called conjugate array. For given a particular partition, you have an array like this. You turn it around, make the rows into columns. Counting column wise, you get a conjugate array. So this actually provides the bijective proof of the statement I made above, namely this last one. Number of partitions into at most m parts, the number of partitions in which each part is at the most. So sometimes we have nice visible proofs, bijective proofs. I will not go much more into the other things because there is a lot of many interesting facts about partitions are there. Let me go to the again. This may be another first results for people to enjoy. Whenever somebody is asked what is the most beautiful proof, maybe they say Euclid's proof of the infinitude of primes. Where sort of very aesthetic and also so simple looking. But it's very subtle. So I myself have not seen anyone who can actually claim that he or she discovered the proof independently. Okay. Nevertheless, it looks like something that one could discover. Okay. Anyway, so in spite of the several advances in prime number theory, many basic questions are still unsolved. I will not go much deeper into it. I will mention in this context, if Euclid's proof is going by looking at the product of first n prime plus 1, this will be divisible by some new prime. So you have given n prime, first n prime, you have n plus 1 prime also. That's how the proof goes. This itself may not be prime. But this question arises, does this happen to be prime infinitely often? This is still unsolved. Many such questions are unsolved. Any of these basic questions about primes are so difficult, very deep, you cannot solve. I mean, they have not been solved. Okay, so let me jump into a different thing. Suppose you take a finite group and we have this so-called Lagrange's theorem. Order of any subgroup divides the order of the group. This is okay, nice enough, simple enough. But the point is that it has many applications. I would say the usefulness of this or the beauty of this result is in its application. So diverse, and I will not mention in detail. I will mention a few things, but not mention many more things which come from this. For example, I just say in words that there is an identity of Kesava Menon, one of the number theorists, beautiful identity, which can be proved using ideas from this that I sort of gave proof of this and generalized it. I will mention that at the end, I guess. But Lagrange's theorem is this. It's very pretty, but what is the accompanying fact here is that groups act as transformations on sets, they transform sets, and the point is each orbit has size, which is a divisor. This is kind of the principal reason why they are very, very useful. Whenever you want to do some counting, there is some symmetry involved. That means some group is acting as transformations, then you can use the group to do the counting. There is something called the Burnside lemma, or some people call the not Burnside lemma because it is not due to Burnside, which is very useful in counting many things, combinatoric. So anyway, so this is the basic thing. So in fact, the Lagrange's theorem is beautiful, all right, and the applications are even more beautiful. So I would just mention a couple of facts. Elementary number theory, statistical congruences, they all follow from suitable applications of Lagrange's theorem. All this Fermat's theorem, Euler's congruence, Wilson's theorem. For example, let me ask somebody who has not seen this. Look at any number A, and any two numbers A and n divides the phi of A power n minus 1, phi being the phi function. Okay. You may be able to prove it using some elementary number theory, but it's an immediate application of Lagrange's theorem. People who are not seeing this as an application of Lagrange's theorem might try. Okay, so I'll go to the next. One more thing. This is again very interesting. Take a prime number p, then n factorial will divide p to the n minus 1 into p to the n minus p, this product. Okay, this also is an application of Lagrange's theorem. If you are told that this is an application of Lagrange's theorem, you will be able to think of what n factorial should denote. It should be order of some subgroup, and this should be order of some big group. That you can think about it. So many applications are there, and I didn't write down anything here about one-side lemma or K-Somanen's identity, but there are many. And then here again, one of the favorites of most people, mainly because whenever we encounter this for the first time, we feel sort of incredulous, something about integers and and we have some pi coming up. How come suddenly it produces pi, which is not even an irrational number, it's a transcendental number? How does it produce this? Of course, the result itself looks beautiful and surprising statement itself. And here I would say that already people like Euler actually gave a sort of proof of this, and I'm going to recall that proof here. Nowadays, you might say this is not a proof at all, but I would. It can be made rigorous. Let me see what the proof is. Okay. Using the same idea, not only you can do summation 1 by n square, you can do summation 1 by n power any even number in terms of some rational number times pi power that even number. Okay, these rational numbers involve what are called Bernoulli numbers. So this is again Euler. Point is, what is the elementary proof that Euler thought of? So think of this sin x by x. Of course, it's not a polynomial, but think of it as though it's a polynomial. So you have an expansion of sin x by x, the power series like this. Think of it as a polynomial. So then you have taken out the zeros of this function are pi, 2 pi, etc. minus pi, minus 2 pi. I have taken out the 0, x equal to 0 here, divided by that. So these are the zeros. So think of it as though you have a polynomial with these roots, because there are infinitely many of them. When you have polynomial whose roots are non-zero, say alpha 1, alpha 2, alpha n, and look at the reciprocal polynomial, its roots are the reciprocal. Reciprocal polynomial is just interchange this a0 to a1, an, and etc. Okay. So this is the reciprocal polynomial. So when you think of the sum of the 1 by alpha I square, you can think of this reciprocal polynomial, because it's the sum of the squares of roots of this polynomial. Sum of the squares of roots we can find in terms of sum of roots and sum of 2 at a time, etc. And you think of your sin x by x as though it's a polynomial and look at its reciprocal. Then you have this what is a0, a1, a2, because they are the constant term for x square, etc. a0, a1, a2. So you get this easy identity. So of course it looks like it's not rigorous, but it can be made. Okay. This is again very unusual. Just because it's so unusual, like sort of beautiful. The look and say sequence. This is discovered by John Conway, who discovered many interesting games and so on. So start with any positive integer. Just avoid the number 22. just start with 1, for example, and just look and say the sequence of numbers. So, for example, define the sequence which just reads out the number of times each chain of digits is repeated in turn. That is, so after 1, we have 1, 1, meaning there is 1, 1. And once you have 1, 1, it means there are 2 1s, right? Write 2, 1. So once you have 2, 1, you write 1, 2 and 1, 1. 1, 2, 1, 1. So you have this sequence. So this is a so-called look and say sequence. What is interesting about it? I just describe it more mathematically. In general, if you have A1 appearing K1 times, A2 appearing K times, etc., AI is not equal to AI plus 1, then the next term of the sequence is defined to be K1, A1, K2, A2, KRA. Okay. So, for example, when we start with 1, we already see 1, 1. There are 2 1s here, 2 1, 1, 2 and 1, 1, 1, 2, 1, 1, 1, 1, 1, 2 and 2 1, 1, 1, 1, 2 and 2 1. 3 1s are there, 2 2s are there, and 1 1 is there. So, go on like this. So, as you can see, the number of digits keeps on increasing. What is interesting is that if dn is the number of digits at the nth stage, then the ratio dn plus 1 by dn, it all approaches a particular constant. Okay, and this constant is independent of what number you start with. Instead of 1, you could start with anything, so the same constant lambda. And this constant happens to be an algebraic number, that is a number which satisfies a polynomial of certain degree 71. Okay, so it's a very interesting thing, and I don't go more into this. I have written a little bit about this in resonance earlier. In any case, these things go under the name of what is called cosmological theorem. So you just cannot start with 22. Every other number leads to the same constant lambda. Here is some problem, tiling problem. Tiling means filling in a shape with a different shape. So suppose you want to fill a square with finitely many triangles. So whatever shape, whatever size square it is, it doesn't matter, because we are just looking at the following tiling problem. The square is tiled with finitely many triangles of equal areas, no matter what the shapes are, but all have equal areas, and the number of triangles must be given. This is quite interesting. I think if I am not wrong, this was given in an exam by someone, or it was proposed to be given in an exam by some instructor, and he found that he could not solve it, and it took a few years to solve later. The point is that it turns out to be surprisingly difficult to solve. And it involves only solution one knows is by using what is called two-adic valuation. So there are something called two-adic valuation, which means for rational numbers, you know what two-adic valuation means, power of 2 dividing that numerator or denominator. Okay. So that is called two-adic valuation. But point is that there is an extension of this two-adic valuation with the same properties, triangle inequality property, which extends the whole of R. This is something quite not elementary at all. But if you assume this, there is such an extension, and use coloring to prove. This is how it is proved. I believe by somebody named Stein. So it's very beautiful and satisfying result. Kind of square is tiled with finite rectangles, triangles. You can try to draw different pictures, different shapes, obtuse, circuit, anything you draw, but all with equal area. Then you can imagine why two-adic will be used. You want to say something is even, so it means some 2 divides something. The 2 is going to come out. So I'm not discussing the proof here, which again will take half an hour. So another tiling problem, which is also kind of very beautiful statement, and I will mention the statement only. So for a real number u, to look at the following thing. You want to tile the square by take the 1 cross u rectangle and then rectangles which are similar to it. The area may not be same, but they're similar to size. So it can be of size p cross tu for any p. Also, any such rectangle you can use, and can use tile a square by this. Okay, for what u is it possible? So it turns out very interestingly that is exactly those u's for which satisfy a polynomial with rational coefficient. So they are called algebraic numbers, and each of its roots has a positive real part. It's not just all algebraic numbers, but those whose roots have all the roots have positive real part. And this statement, 1 and 2 equivalence is difficult to prove, whereas other 3 is there, which is about existence of some positive rational numbers, finitely many of them, so that this, what I have written here is what's called as finite continued fraction. Means T1u plus 1 by this whole thing. This thing is T2u plus 1 by this whole thing. Right? So there are such finitely many rational numbers for which for this u it is equal to 1. So these three are equivalent. Okay, so this can be proved. And for example, this implies facts like the following. The unit square cannot be tiled by rectangles which are of the size 1 cross cube root of 2, the real cube root of 2. But it can be tiled with rectangles similar to this one. I don't think one can just by trial and error discover such facts. Right? You have to actually find what uses are possible. You have to get this kind of a condition. Then only you can think of. So really, these are all the surprise elements. That's why it's beautiful, I would say. Because the statement itself is quite complicated, not so simple. Often the statement is very simple and so very beautiful. It's very complicated, but it's very mind-boggling in some sense. So in the context of coloring proof, of course, we just mentioned in passing the famous 4-color problem. The 4-color problem was that any planar map can be colored with means of 4 colors. So this has been solved, of course. Okay. I'll not go further into it. Just want to say that these are many sophisticated techniques and also a lot of computer checking, large number of cases. So in that sense, I think, I don't know whether one can say that we have understood the proof completely. By the way, if you use 5 colors, it's very easy. It's an elementary exercise to that 5 colors suffice. Okay, then again, this is again a very beautiful looking result. Actually speaking, I would say that it is not very surprising. It's like the definition of pi in some sense. Okay, so I would just not say anything more about the proof of this, but fact is that these things can be used in many ways. It is used everywhere. Gelf and Schneider, they prove this beautiful theorem that certain number power certain other numbers are not algebraic. That is, they don't satisfy any polynomial over integers. So in this context, using this, they prove that e power pi is not algebraic. Using this, okay, this is in a slightly clever fashion. But if you think about algebraicity, we don't even know that things like e plus pi is algebraic or irrational even. So many things are unknown about that. So sometimes more complicated expressions are known to be not algebraic, but less complicated ones are not even known to be rational. So here is again another result. I missed here. There is something missing here. E to the power pi root 163. Pi is missing here. E to the power pi root 163 is nearly an integer. What is meant by nearly an integer? So the adjective nearly here stands for this more precise fact. You look at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 digits are 9 here. Okay, so close to an integer. So what is behind this? And can you find other numbers like 163? 163 will be the biggest such number in some sense. I'll tell you why. This is very attractive and surprising, but proof of this needs what is called the theory of complex multiplication. A lot of things. So I'll just give a brief explanation. Without knowing what is the theory of complex multiplication, one can still understand a little bit about how such a thing can be proved or what is behind it. So this is called the Jacobi J function. This has some nice transformation properties. So when you have I put a tau here, okay, where q is e power 2 pi I tau, think of tau as a point on the upper half line, then j of tau is this function which has a Fourier expansion like this, and there is a negative term also 1 by q, constant term, then q. Positive term go to infinity, okay, there are coefficients all over. So this is j function. So the theory of complex multiplication in particular tells us that when we take tau of particular kind, what is called a imaginary quadratic. So take 1 plus root minus b by 2. B is a certain positive integer which is square free, let's say. Then this number is satisfies the polynomial whose degree is related to this d. So called class number of this field generated by this. In particular, suppose you were to have some d for which this class number is 1, whatever it is, class number is 1, then this will be actual integer. And that is what happens in this case. 163 is the largest set for which class number is 1. And so this value is actually integer. When you put this inside this Fourier series, we get the factors we want. Then feeding this in the Fourier expansion, noting that just q equal to pi I tau, and tau we know the value, so we get this. So this number, as you see, is very close to an integer. Okay, because this number is very small. Q is very small. E power minus pi root 160 equation. That is why it's very close to an integer. In fact, the fact is also related to the following statement. All of you, many of you know that Euler has this polynomial called x squared plus x plus 41. Oh, I think I made a mistake here. Minus 40 and 40 are not included. Started with minus 39 to plus 39. Consecutive numbers. They're all primes. So, this fact is related to the fact that the J value for this 163 is integer. So that's why you cannot find such most polynomials which are, many more bigger numbers than 40. Okay, so let's go to this again, which is one of the very classical results. Fermat's observation. Let's say any prime congruent to 1 mod 4 is the sum of two squares of integers. Very beautiful. This gem is, of course, as I said, due to Fermat, and was an amateur mathematician. As you know, he was a judge, and but this kind of fact, so there is a big theory behind it now due to Gauss, called theory of binary quadratic forms. Where we can talk about whether a prime is represented by some object like a quadratic form, something like x square plus y square. Sum of two squares means it is represented. Value of this x square plus y square, and you put integers. So Gauss had this theory of binary quadratic form, and this much more information it gives. So we say that this is representable if and only if we satisfy some congruence condition. That is the kind of thing that you can show. So in this case of Fermat's case, it is x squared plus y square, and the congruence is congruent to 1 modulo 4. For example, if you want expressibility by x squared plus 3y squared, then you get 1 mod 3. Apart from the prime 3, other primes are 1 mod. These are exactly. Similarly, you can talk about, for example, x squared plus ny squared for a general n, but it becomes much more complicated if it is, n is so that something that I had mentioned slightly earlier in the earlier slide, corresponding class number of imaginary quadratic field is not 1. So that is much more complicated. Which primes are expressible as x squared plus ny squared for a given n? It's a beautiful problem. So I just want to end this point by saying such results are instances of what is called as reciprocity law. So we want a condition of this kind. This is kind of forerunner of a reciprocity law. Quadratic reciprocity, higher reciprocities, and then the most general reciprocity law for abelian extensions is called Artin reciprocity. And even the non-abelian version of that is called Langland's reciprocity, and so on. Okay, so this is the first forerunner in some sense. Fermat's result has a sort of following refinement. So, for example, you look at number of ways of expressing a number as a sum of two squares. This denoted by R2n. Then this number is actually 4 times the number of divisors which are product of prime numbers which are 1 mod. So dn1, n1 is the product of all the prime powers of the primes in the decomposition of n which are 1 mod. And d1n means number of divisors which are 1 mod 4. Number of divisors copy. For Fermat's original result at 1 mod 4 the sum of two squares, there are many proofs, and here is a sort of unusual proof, elementary proof due to Zagier, which I just mentioned. So look at the prime number of the form 1 mod 4, that is 4n plus 1. So look at this following set. We are looking at 3 tuples x, y, z, so that x square plus 4yz equal to p. Remember, when you have prime number of this form, then if it is x square plus y square, one of them is going to be even, the other is going to be odd. So that's why you look at 4 times yz. And suppose you have a point here which is where y equal to z, then of course you have an expression for p as x square plus 4y square, sum of two. So this is the idea. So point is, how do you use this set? What Zagier did was the following idea he used. explicitly produce an involution of this set. That is, the transformation of this set is of order 2. Permutes the set and the permutation is of order 2. Whenever you have permutation of the set of order 2, is a finite set, you can just pair together a point and its image. Unless the point and its image coincide, which means the fixed point. So precisely, if you leave out even number of points from this S, you are left with the fixed point. Okay, so the set will have how many elements? Parity of this set, cardinality of this set will be parity of the number of fixed points. Involution, if you can find an involution. So Zagier wrote down an involution explicitly like this. It's a bit complicated. It will take one more kind of lecture to see how you can think of such a mapping. But you can explicitly, once it is written down, you can check this is order 2 and it has a unique fixed point, namely this 1, 1, n is a unique fixed point. Okay, and once you have once you have proved this, that means your set S must have an odd number of elements, as I said, because non-fixed points can be paired together. And so, because of that, so as I said, it's odd. So now look at this permutation, which is an interchanges y and z. Since for this is also of order 2, which means you can pair off point and its image, and you are left with singletons which are fixed points. Since after pairing, you should be left with at least 1 point. So that are at least 1 6. The fixed point of this is precisely as we mentioned, an expression for P as x square plus 4y square. Remember, when you have fixed point of this, y equal to z means x square plus 4y. So there are versions. There are the other versions due to Heath Brown and Mohan Nair. I don't go into. I mentioned one more. Brouwer's so-called fixed point theorem continues the function from the unit disk. This is the unit disk, so itself has a fixed point. So some people find this very beautiful. It is also mentioned as one of the results, but yeah, anyway, so it is nice. What is the one-dimensional counterpart of this? It is the interval -1 to 1. So for this, if you look at the same fact, a continuous function from closed interval -1, 1 to itself has a fixed point. This pictorially you can even see of this. So this is a two-dimensional counterpart. Brouwer's theorem. Brouwer's theorem has many interesting applications. For example, you can show the following thing. Look at a continuous function from Rn to Rn, the general n, and see, suppose a positive, still I have taken R2 to R2 here, anyway. C is a positive constant, so that the distance between fx and x in Rn, okay, is always bounded by, so like it's in a tube, fx and x, now mod of fx minus x, mod in the sense of Rn is at the most C, then f must take all values. So this is ontoness. So this is an easy application of Brouwer fixed point, which you can work out. Oh, okay, I have still given the proof here. Take this constant g given by this and apply your Brouwer fixed point theorem, this continuous one. You can show that this takes the disk of radius c to itself. So a fixed point precisely tells you that every point y has this image. So the nice application. So I just mentioned one more result in passing, so called you cannot comb the head of a head which is perfectly spherical, their straight hair. It is called hairy ball theorem. This is an application again of Brouwer and so on. Now in the similar ideas, not Brouwer fixed point theorem, but similar ideas. So it actually means that there is nowhere vanishing vector field, tangent vector field on the unit sphere S2, 2 dimensions. Again, it is related to the fact that Euler characteristic is not 0. Anyway, so let's go to the one more application. There is no equilateral triangle over the plane with all vertices to be. Let me see. I've reached 8 now. I think. How much time can I take? No. Can I take another 5-10 minutes?
Sure, sir.
Yes, sir.
Thank you. So there is no equilateral triangle on the plane with all vertices as lattice points. This is very trivial to see. Why? Because when you join, when you look at the angle between them, tan theta, for example, has to be rational, because slope of any line joining two lattice points will be rational. Because of that, tan theta will be rational, which means tan of 60 would have been rational. But in free space, there are many such lattice triangle. They can all be characterized by solutions of a Diophantine equation. What is the Diophantine equation? I just mentioned here on the plane this is not possible because tan 60 is irrational. Okay. You take two lattice points, line joining has rational slope, so the triangle would have tan theta would be rational. So for three-dimensional, for example, here are some examples. These are all lattice points, okay, and it's an equilateral triangle. As you can see, the distances in R3. In fact, the length is of this form. This should give an idea about what Diophantine equation you are going to arrive. You can translate the vertices by an integer vector so that for a triangle there, one of the vertices is the origin, and there are two other lattices. Suppose you do this, I just want to give a description of the Diophantine equation involved here. So look at O, P, and Q. The area of this triangle is given by this determinant of this matrix, which is of course also when S is the side length, and it is, we know that it's going to be S square root 3 by 4, which means we have this formula here: x square plus y square plus z square is S square, and u square plus v square plus w square. Determinant here gives the area as the length of the vector OP cross OQ. You can view it as a length of the vector. Because of that, in terms of the usual ijk unit vectors, whereas OP cross OQ as in terms of ijk coefficient A, B, C are in terms of the x, y, z, w explicitly like. Okay. So we have this area is the length of this vector, which is AI plus BJ plus CK, and ABC are explicitly like. Which means, see AI plus BJ plus CK. That means this is in the plane orthogonal to this cross product, of course. So it's on the plane. So the vectors are on the plane AX plus BY plus CZ, which is orthogonal to the cross product. Writing S square equal to 2D, we observe that the length of the vector square is S square, which is given by this. This shows that we have this kind of formula. And finally, I just want to very quickly say that putting the values ABC, we have this. This is the Diophantine equation. Actually, initially I wanted to include a full proof of how to find all solutions of this, but I just mentioned that this has many solutions. Solving this is precisely solving all lattice triangles in R3. Equilateral lattice triangle. Okay, so for example, this is of course this is a class of solution, but we have other classes. For example, you put minus 19, 11, 5, and you get bizarre looking triangles. Okay, they're all equilateral. All of them have vertices on lattice point. So this is again a different, nice different theory. I guess this is the 14th application, 14th beautiful result. Consider this any quadratic form. Quadratic form is an expression of this form. So summation, the quadratic form is a quadratic here and homogeneous like this. So where these integers, aij's are integers, and suppose we have the following property. Alias takes only positive values of all integers, except that means this is called a positive definite quadratic form. I just mentioned it as takes only positive values. Okay, then there is a beautiful theorem due to Conway-Schneeberger, which is that suppose there is a form which takes all the values from 1 to 15, then it must take all integer values. And not only that, you cannot reduce 15. Okay, there are things which take all the values from 1 to 14 or something like that, and do not take all values. 15 is. In this respect, actually, Ramanujan's work also one could mention, which I have not included here. There is something very interesting, and he talked about quadratic forms in 4 variables and tried to find out all which are universal, ax square plus by square plus cz square plus tw square, like that, which are universal, take all values. We know that every integer is sum of 4 squares. So x square plus y square plus z square plus w square is universal, take all integer values. Similarly, Ramanujan found all such forms. In his list, there was only one mistake. I think list of 55 forms, if I remember right. One of them is has an error, and that is simply because it's missing the number 15. That is why it's very interesting. This 15 is crucial. And this proof was never published, I think. It's supposed to be published in Inventionist, but I think a simpler proof has been given by Manjul Bhargav when he was a graduate student. So, of course, there are, Bhargava has other theorem called, this is the 15th theorem, there is a theorem called 290 theorem, 290. I'll not go into it. So, finally, this is the last one I want to talk about before, prior to the completion of the so-called classification of finite simple. So, classifying finite simple groups is something like, classifying elementary particles. So, it's a kind of, but of course, it has been done with a large body of work, and the people are still trying to simplify so that you can understand it as in simpler ideas. So, usually people used to predict the existence of a group with some properties. And for quite a few years, people will be working towards proving the existence, and finally it will come out. Similarly, in that vein, such a prediction was made for a huge finite group, and by Fisher and Grice in 1973. They made this prediction in 1973, and finally this is produced. It's called the monster. This is the biggest finite simple group. Its order is around this size, 8 cross 10 power 8 times 10 power 53. The Fisher-Grice monster is called one of the finite simple groups. Okay, simple group means something which does not have any non-simple group. So it's sort of like a prime number. Think of it like that. So point is, in 1980, that is 7 years later, he constructed the group as automorphism group of a certain algebra. This algebra is this dimension, 1,96,1883. Why am I bringing this number? If somebody was in very alert and had seen my earlier slide, will also know, would have noticed, but I'll recall again here. Mackay made this beautiful observation, or amazing observation, surprising observation. 196,883 plus 1 is 196,884. This is not the observation. The fact is that 196,884 occurs as a Fourier coefficient of the J function. Okay, this may be just an accident. Look at this 21493,760, other mixed coefficient. Okay, so this actually happened to be the dimension of the smallest irreducible representation of the monster. So whenever you have a group, you represent them as matrices, and what is the smallest dimensional irreducible representation? That dimensional matrix is this matrix, and then as we said, this mixed coefficient is actually the sum of these numbers 2129,876, and next is this sum. In other words, left hand side is Fourier coefficient from J function that we saw. The Chekhov is J function. The right hand side gives the dimensions of irreducible representation of the monster group. Totally different things. One is a monster, other is the J function, which is no relation with each other. But he noticed it, so it can't be by accident. So Conway and Norton made a very bold conjecture, some very bold conjectures which are called, go under the name of monstrous moonshine. Because we know the monster, it's called the monstrous moonshine. Why is it called moonshine? The moonshine is supposed to be slang for unreal or idle speculation or sort of an elusive shadow. It's also said to be a reference to in Shakespeare, Midsummer Night's Dream, where he used this phrase. Something which is crazy or unexpected, he used this phrase, moonshine. The monstrous moonshine theory was an amazing and unexpected connection between two seemingly different areas of mathematics, modular functions and representations of the monster group, where the bridge came from physics actually. Informal field theory was the bridge. That's how this proved actually a whole hidden world emerged from here, and finally it is Conway's PhD student, Borchardt, who proved this conjecture. He won a Fields Medal for this work, and Borchardt said apparently that after proving this, I was over the moon when I proved the moonshine conjecture. Okay, so I would kind of end here, but before ending here, I would beg your indulgence and say, let me also share some very elementary observations which I thought were beautiful, and let's see whether you agree. So a result can look beautiful even if it is not very difficult to prove or anything like that. But it looks beautiful. So let's see. So here is an observation. For arbitrary positive integers nr, so just take for example even r equal to 1. Okay. Summation minimum is summation I. Summation minimum I1, I2, IR is summation. Similar such relations exist for maximum and some there are polynomial versions. This looks very pretty. Let's think for two things. Summation minimum ij, like that. I and j go from 1 to n, is summation I square. With generalizations I mentioned. On one more I mentioned, which is that you have such polynomial identity. There are plenty of polynomial identities one can look at and very elementary to prove. Once you write down one identity, it is of course high school algebra to verify it. Okay? So once you look at the identity, once you prove such an identity or obtain such an identity, then you can specialize values and get some nice relations. One of them involves the Fibonacci and Lucas numbers, Lucas sequences, such a nice relation here. So seem to be new actually. Remember what the Fibonacci and Lucas sequences were? They are all defined by the same recurrence relation, but starting points are different. This is a nice relation. And here is another expression for Fibonacci numbers and Lucas numbers in terms of trigonometric functions. This also looks pretty, not very deep. These are all very elementary, but I hope beautiful. So here is one more example. Look at numbers a1 to an. So look at the ratio product of ai minus aj by I minus j. Okay. I is bigger than j. So you're looking at all this product of ai minus jj, I bigger than j, divided by product of I minus j, I bigger than j. Everything going from 1 to n. ai's are arbitrary, distinct. Then this number actually, which is a positive number, is actually integer, positive integer, which is the dimension of certain representation group S2n. So you can try to prove that this is actually an integer elementarily, which you can do. You can use some van der Waals determinant and so on. But one can also prove something like this, polynomial version of this. One can prove this. So you take a variable q and look at this thing, which is a kind of counterpart of this, polynomial counterpart. You can show this is a polynomial with integer quotient. And when you take the value at q equal to 1, you can apply L'Hopital's rule, for example, L'Hopital's rule to find out, you can obtain this integer property from the integer polynomial. Evaluate this integer polynomial at q equal to 1. Okay, and you get this integer. More interestingly, look at Gaussian polynomials. These are the analogs of binomial coefficients. They are defined like this. They are polynomials actually. Although they look like ratios of polynomials, they are actually polynomials. In fact, they count the number of, if q is not any variable, it's just a prime power or something like that. You can think of the field of q elements, the n-dimensional vector space, they count the r-dimensional vector spaces, how many they are, counts that. So these also satisfy some relations like binomial coefficients. And using this, one can show that if you take a polynomial whose, matrix whose ijth entry is ai to j minus 1, ai is being arbitrary integers, like this, then corresponding polynomials are entries here. So when you take determinant of a polynomial, determinant of a matrix whose entries are all polynomials, then you get a polynomial. So this determinant happens with this polynomial. So it shows that here is a polynomial. From here you can again prove that what were we claimed earlier. So finally, as I said, group actions can also be used for many other things. I mentioned at the beginning that this one-side lemma is used. For example, one can use it to prove an identity of this form. This generalizes a beautiful result of Kesselman. And I wanted to give a proof of Kesselman's identity using group theory, and I noticed that I can get something more general. This is another element. But since then, a lot of people have discovered many more identities of this. Okay, I think I'll stop here. Thank you.
Thank you so much, sir. It was truly amazing. You know, when something is really interesting, the time flies, and it really happened here. I'm remembering the golden ratio, and then it was like totally fast. It like we didn't know that the time is like going on, and we can see the responses of audience here. They are really happy, and also people started chatting in the chat box. So
I can share this file with people. So okay,
that
so
is so kind of you, sir. Okay, so thank you so much again, sir, from deep of our hearts. And now we are going to the interactive session where the audience can switch on their videos and interact with the main speaker, the Dr. Professor Sury today. But before that, let me just mention graceful presence of some of the senior professors, Professor R. Balasubramaniam sir and Dr. Preeti Kutipilakal. So we are truly grateful for your presence here. And now, Vinod sir, can we move to the interactive session?
Yeah, Arjuna, there are some more professors. I think we have, I think Vijay Kumar sir can name them.
Guide us.
Yeah, it will be great if that senior professors can share some of the comments. I think R. Balasubramaniam sir is there, I think. Yeah, otherwise you just move on to.
Okay, sir. So if they are ready at any point, we are totally welcoming to hear from them. So now we are moving to the interactive session where the participants can ask any questions or share their experience with us. But please remember to turn on your video before you start
First
speaking.
of all, let me say that it was a beautiful lecture, bringing out some beautiful theorems. But unfortunately, the proofs or even the statements or generalization do involve a little higher mathematics, and therefore you are not really in a position to explain those things. But at least for the sake of the youngsters, would you be able to add some references of what on everything that would help them to, when they want to really learn a little more, of where to find out the other material? Of course, some of them are already covered by you in resonance, but generally, even if you can do some references, that would be very nice.
Well, thank you. It's really high figure coming from you, and definitely it's a good idea. I didn't think of that earlier. Definitely, I'll add some reference.
Thank you, Balasubramanian sir. So now it's time for you, dear participants, to speak out.
Uma has raised a hand. Yes. Athena, please go ahead.
Sir, can I ask something?
Please go ahead.
It's not a big question. It's something I really wanted to know from you, because our topic is beauty in mathematics. You told about some unknown things and unknown theories which doesn't have proofs. So out of all these, do you have any favorite which is more understandable to everyone here?
Oh.
Like, seems like very silly, but it's really hard to prove.
Yeah, no, there are so many things. Especially in number theory, you can mention. Professor Balu will tell you that hundreds of basic questions you cannot answer because they are so deep. Suppose you want to know, are there infinitely many prime numbers which are n square plus 1? Okay. For example, it's tantalizingly close to saying sum of 2 squares. It's not that. It's square plus 1. Quite far away. Nobody knows. Of course, some of the big problems people have made big advances in prime. Okay, so if you want to talk about what is known, it's very deep again. So number theory will give us several such examples. And yeah, I would sort of stop at number theory.
Yes, sir. And isn't it fascinating to chase these kind of things which are really unknown even this day, and it really becomes a beauty for the subject?
Absolutely. In fact, I would say in our lifetime, my lifetime, lots of things have got proved. I feel that the previous 50 years, what was proved, and after I was born, what has been proved, quite a few big problems have been proved, questions. And one of the beauties about mathematics, I feel, is that when some very deep problem is solved by someone, parallelly, some other people also give other proofs. So why does that happen? My own feeling is that because things have to mature and come to a level where they can be applied and come to fruition. But also the belief, psychological belief that yes, oh yes, this can be solved. So then they put more effort and then no. I guess many big problems have got solved in the last 50 years. We just see that number of problems got solved. Of a Hilbert problem, how long it took for several things, and now after that in the last 50 years.
True, sir.
Yeah,
And
that
what
is
would you recommend as a resource for
You
us?
saying something.
that is completely true. And in fact, yeah, the progress probably has been rather rapid in the last 20, 30 years. I mean, things which we didn't even expect to be proved have been really proved, and I mean, in some sense, a golden period in mathematics.
Sury, in one of your slides, you mentioned about the infinitudeness of prime numbers, and you mentioned that you have not seen any independent proof of that. What did you mean by that? I've read somewhere that there are.
I have personally met someone who says I have independently discovered that proof. That Euclid's proof.
Okay.
Euclid's proof itself, many people would say that, oh, I could have discovered it because it's so simple. But in reality, I don't know whether anybody has actually discovered it. Balu will tell.
Yeah, no. I mean, exactly. Let me repeat that. I mean, there are really many problems where you try hard for maybe even 10 years, 12 years, and then ultimately you see somebody has proved it. Then you go through the proof, and you realize you could have proved it. I mean, you had all the necessary things with you, but still you didn't prove it. How did I miss it type thing? And this is one thing he was talking about, the Euclid's proof. Once somebody explains to you the Euclid's proof, you think there is nothing really much in it I could have proved. But on the other hand, before being told about the Euclid's proof, nobody seems to have come to the same proof independently without seeing the proof. I mean, it is so easy. When you look at it, you say you could have proved it because the ideas are not too deep. But I don't think anybody has proved it before seeing the Euclid proof. That's what Sury says.
Hello, Hasina. I think you have some questions. Ajuna, please ask once again.
Yes,
People
sir.
are raising hands.
Yes, dear participants, please make use of this opportunity to interact and ask your questions.
One more thing, I just want to come back to Arjuna's question about results, which are very surprising and old and all. I mentioned only number theory, but
Yes.
Ramsey theory, very little is known. Such a simple looking problem, Ramsey numbers, and very little. Very recently, I think R44 or something was found. Very few things are known. Sorry, go ahead. Anybody asking questions?
Thank you for that, sir.
Hello, sir. Hello.
Hi,
Yes,
Arvind.
your voice.
Thank you, sir, for your most valuable lecture. This is most expensive lecture. So, sir, I have a short question about this. At the starting of this lecture, you have used that Jordan curve. So, I have a question like that. What kind of curve is that Jordan curve?
Okay. So basically, a simple closed curve without self-intersecting. Simple closed curve. So you can have many sheets. Since I mentioned it in the context of Venn diagrams, I can probably share with you some article which tells you what type of shapes are allowed in that. Okay. Many more types of curves are also allowed for drawing Venn diagrams. Sometimes it looks like rectangles. Okay. So there is a whole family of things, not just Jordan curve. Other things also you can use for Venn diagrams. Jordan curve itself is just, I just mentioned it because it does not have to be a circle. That's why I mentioned it. But it's not as though for Venn diagrams you need Jordan curve. You don't need it really. Other paper. I'll share an article. That's
Okay,
actually
sir.
good, interesting thing.
Okay, sir. Thank you.
Good evening, sir.
Good evening.
Sir, am I audible?
Yes, yes, you're audible.
Sir, thank you for the great session. Most of the topics were new to me. I'm an undergraduate student, so some of them went above my head, but overall it was really interesting. Sir, I have a query. Like us students, like we are having a lot of syllabus, and like most we are like asked to stick to that. So in a way, we are like kept away from the beauty of mathematics. So I would like to ask you, what is your take on the undergraduate research and things like that?
Very good question. Very complicated because, every summer or winter vacation, students come and do undergraduate projects, whatever, summer project, winter project. So at that time, since there is a break, they try to do this. And in my own case, I sometimes have 15, 16 students in the summer staying and doing projects with me. But in general, during the semester, it's very difficult for students to cope up with the syllabus, whoever it is, however bright they are. And some of them are very enthusiastic, and so they start doing this. And I would also agree with teachers that the syllabus is there, to concentrate on that. They are very comfortable with it. You do some general reading, but don't really get lost in it. And if you are in touch with some of the people like me and other people who are, sometimes take summer students and all that, even without, physically coming to my place, we can be in touch by email, and I have, supervised many people's projects. That way, the person who knows what somebody with this undergraduate background or second year background, let's say, might know, can give a project. Then you can kind of do that, because it has to be done very carefully. Otherwise, what will happen is you see from the internet, you just pick up something is very complicated and it is not practical, or something very, very fashionable, but it is not such good mathematics. Maybe if you are lucky enough to be in touch with some of the people, Prof. Vinod Kumar and other people, then they would guide you as to, whom to approach, and they will probably tell you some people who are willing, maybe Professor Kalyan, Chakrabarti, all these people, they will tell you what to read and what they'll give you something. So once you develop that, then you'll feel more confident about during the semester itself doing extra reading. Because I am always cautious about doing extra reading during semester. I mean, doing some research during the semester, unless it's part of the curriculum, it's going to be difficult. You will end up neither learning this nor learning that. My feeling is that. If Professor Balu wanted to say something, I think. He vanished.
Thank you,
No,
sir.
you explained well. I have nothing more to add.
Praveen, where are you studying now?
Sorry?
Praveen,
Sir? Yes, sir.
where are you studying?
Sir,
Oh, it's not audible.
Hello, sir. I'm audible.
Yes, become.
Hello,
Yes,
From
sir.
Gajendra Singh.
Yes,
sir. I'm yes, sir.
I'm a
I'm
third
speaking.
semester student at St. Thomas College, Thrissur.
Okay.
Hello, sir.
Now,
We will keep in touch.
Hello.
yes.
That lecture was awesome, and thank you, sir. Actually, I have taken your lecture before in this type, and whenever I take this type lecture, then I feel good, and I have taken more knowledge about mathematics. So thank you so much, sir.
Thank you. Actually, for me, what matters is your enthusiasm, because most of the time you are yourself the one who kind of you're responsible for how much time you spend, what you do, and once you feel enthusiastic, you will go back, and that matters. What, despite whether you followed, when people follow too much or enough of this or not half of this, quarter of this, whatever it is, but if you go back with some enthusiasm, that really matters, I think.
Yes, sir.
Thank you, sir.
Good
So when
evening,
you
sir.
talked about spending time, I had a question which might be useful for many here. Do you suggest any resource we can check on a daily basis to get more updates about mathematics?
I'm not sure about such thing as common source resource where you can daily updates or very regular updates.
Or maybe not
Can-
daily, like in a regular basis,
Yeah,
which keeps us updated.
things like there are there are things like in India there are certain magazines and journals which have articles, but it doesn't really give state of the art, huh? But which are kind of enjoyable and readable. At a high school level, there is this journal called At Right Angle, very nice by Azim Premji University. But it also has articles at a higher level, and they are very well done, beautifully done. And Resonance also has, and mathematics students, which is supposed to have lots of such articles, I think once in a while it has something which is reachable. Every issue of mathematics students should have some articles readable for students. Okay, these are all, but not necessarily exactly what is happening right now. But still you can learn some subjects, some topics. I would say I myself check it through, when news comes to me through some sources, people that I know, or notices of AMS or things like that, or, in the internet you have mathematics news. So half of them will be, just somebody saying something, but I don't find a source which has, resource really which is very trustworthy and, can particularly pick up. But I will think about it now that you told me. If I can, I'll try to find few sources and share with you.
Thank you so much for your time, sir. And now, sorry for making you wait, Aryan. You may please proceed with your question.
Okay, thank you. Sir, the session was very interesting. And my question is, sir, that after Ramanujan, we cannot name any great Indian mathematician. Like you studied from Sir M.S. Raghunathan, but I have to speak in my university for history of Indian mathematicians. So I was thinking why these Western mathematicians are like Gauss, and a lot of them are there. But when it comes to India, we have, although everyone is working good enough, like you are also a great professor, like whomever I study, he's also doing very well. But why uh, I means I think you got my point. And so one other thing, like. What I want to ask, when we are doing our courses, so lot of things are interesting. Like whatever I study, I feel interesting in it. And then there are a lot of things. So how to choose something when I am studying real analysis, then I feel good about it. When I start topology, then it's also very interesting. Linear algebra is very interesting. Group theory is also very interesting. So, but like time is also constant. So it's how did you do in your times?
Okay, so there are two questions. So first question I want to tell you that I don't agree with what you're saying that after Ramanujan there is hardly anybody. Ramanujan might have been very, very unique because you cannot imitate him. But as Professor Balu is here, he will tell you, he's given many talks also about how many mathematicians from India have, shown in the all over the world. So, see, Ramanujan is unique because of the romantic story behind his background and what. But in the modern world, there are many, many mathematicians of Indian origin. Some people living in the US also or other countries, Europe and other places, but in India also, people have broken ground who proved seminal results and people are so unfortunately the public does not know about them. So in the mathematics community itself, we have to popularize that. There are many names. So maybe one should give a talk about modern Indian mathematicians after Ramanujan. I'm sure people like Professor Balu has given talks on this. There are many, so I cannot really, agree with what you're saying, and at the same time, I cannot give you many, many names. There are many. I'm sure people here would agree that Vinod Kumar and Ramaswamy, everybody will agree with that. There are many Indian mathematicians, so known all over the world. You should not compare with Ramanujan because even if you remember, Hardy himself said when he compared Ramanujan with Littlewood or himself, he thought Ramanujan is
Yes,
much
sir.
higher. So, but it is he was unique. He's inimitable. You cannot try to imitate. That is a wrong thing to do. But even someone like Rish Chandra, people don't know about. He is probably as great as Ramanujan in some sense. Okay, many people like that are there who are very good mathematicians, top mathematicians all over the world. They are the leaders in this topic. But I think one should have a talk about them.
So,
And you
like,
talk about Gauss, people like that. Gauss is, so in the earlier situations, of course, we had Bhaskaracharya and people like that.
Madhva.
In the ancient Madhvacharya, many people like that. And there was a break, kind of break. But in the modern times, again, there are different. But that's I would not go more into this first question, except, I mean, I want to give a talk on who are the people. I'll give you a lot of people as to say what they contributed. Instead of just naming names, I should tell you what is the context, what did they do, where does their work stand. Then you will realize, yes, there are people who are even still who are alive. Okay, that's the first thing. Second thing is, again, how to choose what you like. In fact, the dilemma that you mentioned, I also faced. I also first saw something, some analysis, and I thought, oh, it's the most beautiful. I want to do the analysis. Then I saw some number theory or number theory. Topology, group theory, anything is that this is what I want to do. But at some point you realize that, okay, it's like a food counter here. You take a little bit of each thing, but at some counter you have to settle and pay. So you have to decide at some point and go. But what you decide, it's not going to be bad, because anyway what you decide is something that you like. But you'll have to sacrifice certain other things. Nevertheless, when I decided, I thought I should think about Lie groups and number theory and things like that, which is central. Lots of areas of mathematics are coming in there, whether it is group theory or analysis, topology, number theory. So that kind of combination, I like that kind of central area. Whereas some people go deep into one thing and they may not really get seriously into other matters. So they are losing out in some sense. Nevertheless, their contribution is, very good in that particular area. So some people are made for that thing. You just go into one area, and suppose you are a combinatoric person. You have to know many other areas to know that, to do that. But you also go deeply into one thing, so you don't know many other areas in the what is done, state of the art, you don't know. But what you would know, the kind of ideas which is common to most of the mathematics. So at some point you have to choose. There is no question of that. You have to choose. There is no good royal road to mathematics.
Thank you. Thank you, sir.
Hello.
Yes, Sachin.
Yes, sir, this was a great talk. I had two questions. First is out of all the results, I found that e to the pi root 163 the best one. And I wanted to ask, sir, you told that j invariant of 1 plus root of minus 163 over 2 is very close to being an integer. Is it true for the other Heegner numbers as well, for which the class number is 1?
Yes, exactly. It is true. That's correct. So j is the value is actually the ring of integers of the corresponding number field. Class number is 1 means it will be an actual integer for all these other points of wherever class number is 1. But there are only finitely many. See? And
Yes.
163 is the largest one.
And sir, you told about that monstrous moon sign, that the bridge to the field of this J invariant and this monstrous group, monster in the sense of size, comes from physics. Could you throw more light on that? Like, how is it?
Oh, so what I would do is, since I am not a physicist, but I know a little bit about how the connection goes through conformal field theory, but I'm not suitable. I mean, I'm not fit to describe it in a small thing like this. So perhaps we have an article recently, maybe a month back, we had an article by one person who is a physicist, mathematical physicist. In resonance, I'll draw attention. You look for the his article in resonance, even if you search. Otherwise, I'll share with you. Okay. There he describes the physics part, not too much because resonance is an undergraduate level, supposed to be like that. So doesn't do too much, but it gives references and go more into it if you are interested in physics. For conformal field theory is the bridge check.
Thank you, sir.
Thank you.
Apologies to interrupt. Participants are advised to say their name and what they are doing right now or their place before they ask their questions. And please switch on your video so that it would be a pleasant experience for all of us. And some people have already raised their hands. If they are ready to speak, you may please proceed.
Okay,
evening,
sorry.
sir.
My name is Sachin, and I'm in BSc Math course at VIT Vellore. I'm in my second year.
Thank you, Sachin.
One second, Sachin, your Professor Vanchinathan is teaching you?
Yes,
No.
sir. I'm in contact with him. Like, he shares me questions sometimes, and I solve them via emails. T. Vanchinathan. He's in VIT Chennai, sir. I'm in VIT Vellore.
Okay, thanks.
Good evening, sir. I am Shikha Kumari, and I have completed my integrated MSc in Mathematics and Computing from Birla Institute of Technology, Mishra, in Jharkhand. So your session was really wonderful, and especially that Venn diagram, it was really interesting to see. And so thank you for taking out time for us and inspiring us. Sir, I have one question. Since I've taken a drop and preparing for CSIR NET exam. So, student like us, how they will spend their time apart from preparation for any research, for their contribution in research, or any activity to follow, so that they join any research institute in future, that it will be helpful for us in future.
So, as I understand, you have taken a drop so that you can prepare for the entrance exam, right?
Yes.
Right. So, it's a very difficult time because you have to prepare and you have to wait. Now, you should not be out of touch with institutions. So, if possible, I would always recommend that if whether it's your earlier alma mater like BITS, Jharkhand, or other places where you have some contact, you can attend some classes and so on. That's what I would say. Being out of touch and just sitting and preparing, it's a difficult job, keeping your motivation. I don't know what to say for that. So I generally always recommend people to be in touch with some institution, or at least somebody who is attending that, look at that, discuss with them, things like that. It may be a research scholar who is already doing research there. Maybe try to find some friends. I know it's difficult. It's not so easy to find someone. But if it's a parent institute, you may be allowed to attend some lectures if it is possible. Then you are in touch. So you feel part of the ambience. Otherwise, sitting by yourself, you don't know how well you're doing. You can't attend just internet lectures. Right? And, internet, of course, there will be a lot of things. You can attend YouTube talk, attend other things. But I would say go physically to an institution and attend some lectures if possible. Until if there are colloquia and so on, attend that. And be in touch with some people, some students. This is the best I can say. I don't know what else to recommend for that.
Okay, sir. Thank you, sir.
Hello, sir. I'm Gayatri. I have done my graduation from Miranda House College, University of Delhi. First of all, thank you so much for your valuable time, and you have shared a lot of interesting points with us, and we are really grateful to have you, sir. And Vinod, sir, thank you so much for organizing these kind of amazing webinars all the time. Thank you.
Thank you.
I am Dharmendra Singh, sir, from Kasganj. I am preparing for IIT JAM. Before this, I was doing library technician job in BARC. I want to know about Diophantine equation and relation with triangles. Can you tell more else?
Okay. So, anything is, in some sense, when you talk about Diophantine equations, any problem can be created, made into a paraphrase as a Diophantine equation. Okay, really speaking, most of the problems. But some of the times, naturally, some Diophantine equations arise. Triangles and so on. The one I talked about was for tiling. The Diophantine equation was a square plus b square plus c square equal to 3d square. But in general, Diophantine equations arise in many geometric problems. For example, I would mention more centrally something called the congruent number problem, which is still not solved completely. Okay, so this is a following problem, which is that what are the positive integers which appear as areas of right angle triangle. All of whose sides are rational numbers. Okay, both the legs and the hypotenuse are rational numbers and areas and integers. Such triangles, what numbers occur as areas? They are called, such numbers are called congruent numbers. This is the oldest mathematical problem in some sense. So this gives rise to problem, a natural Diophantine equation, which is number n is the congruent number if and only if the Diophantine equation y squared equal to x cube minus n square x. Y square equal to x cube minus n square x. Okay, in this Diophantine equation, it has some infinitely many solutions. Okay, so next thing, and the solutions are looking for over rational numbers actually. Okay, I should say that. So these are special kind of Diophantine equations. They are called elliptic curves. So this elliptic curve arise naturally in many situations, and congruent number problem is still not solved. Many things are known, but still, what are all that? What is the characterization? Complete, necessary and sufficient characterization of congruent numbers. So this is the certain Diophantine equation. So, and many other problems have many other Diophantine. We know that Fermat's theorem, and can think of other equations of this kind. Sometimes Fermat-like equations can be solved, and many other. If you talk about x power a plus y power b equal to z power c, many open problems are there. You don't even know how to go about it.
Thank you so much,
Thank you,
sir.
One question also. You discussed two adic number. This is related to p adic number.
So what is the, yeah, everything, see, okay, this is, since you asked this question, I might as well tell, whenever we do any kind of number theory problem, you want solutions over integers, you are forced to go into something called, often forced to go to something called p-adic number. Because it's like this. You know the elephant story where, somebody touches, blind people touch that this is a tree and it's a trunk, trunk of an elephant, tree of an elephant, touch, tail, body, and so on. Each of them touches a different part and looks different. Okay. So here also, all the, whatever you are asking about what? The p-adic numbers, right? So p-adic numbers is like this. Over rational numbers, you want to understand rational numbers, you have to look at what all notions you are putting rational numbers as part of real number. Okay, and why are you doing this? Because you want sequences to converge. Then you put a completion, like you have Cauchy sequences converging. So, but there is the other notions of distance between points where we can converge and so on. So, to understand rational numbers, you have to study all possible notions of distance on integers or rational numbers. And one of them, for every prime number, there is a notion of distance called p-adic distance. So, only if you know that all of them, then you can put them together. So, integers are much more difficult to study than p-adic numbers. Okay, because there is some kind of completion is there. Just like real numbers, you have Cauchy sequences converging and so on. Rational numbers will not happen, so it's more difficult. So you have to gather all this information together to come and deduce something about integers. So you have to say something called p-adic numbers. For example, suppose you take what I mentioned, quadratic forms in one of the examples. Look at a polynomial like ax square plus, polynomial in some number, say 5 variables, and which is a quadratic polynomial, homogeneous quadratic polynomial with rational coefficients. You want to know whether it takes the value 0 at a point which is at some values of the variables which is not 0, 0, 0. Some other point, does it take the value 0? So this is equivalent to whether it takes the value 0 at real numbers, and you put real values for the, and also p-adic values. So this is called a local global principle. So to understand global problem like over integers, you have to go to these local places. Like each known as a direction, p-adic direction. So each is a local. There it by itself, it's a local thing. Everything else doesn't exist. Everything is like a unit. So p-adic numbers are very essential to study integers.
Sir, okay. Thank you.
Hello, am I audible?
Sorry, so due to time limitation, we would be
Yeah.
able to.
Arjuna, let Lakshmi speak. Lakshmi is from Hansraj College, the degree institution of Sury sir. Yeah,
Sure,
Lakshmi.
sure. So I was saying we will be winding up after 2-3 people speaking.
Yeah.
Thank you so much.
Good evening, sir. Am I audible?
Yes.
Hi, sir. As Vinod sir mentioned, I am from your alma mater, Hansraj College. It was really, really nice hearing you live. And I'm actually in my final year of undergraduation. So I got some of the concepts that you were explaining. Some of them did go over my head. But it was really nice, there were some of the statements which I had heard, but I had not come across the rigorous proof. So it was really nice seeing those, seeing the proof really helps you get the concept really well. So it was really a wonderful session, sir. Thank you so much for sparing the time.
Thank you.
Yeah. Yes, I think Professor Ramaswamy is there.
Yeah, can I?
Yes.
Yeah. Hello, Sury. How are you?
Nice to see you. Very nice to see you. 35 years now.
Yeah, my name appears to be in my wife's name.
Yes.
Okay. Yeah. Very nice talk, Sury. Yeah, very nice. You and Vijay Kumar should meet at least sometime now that it's almost 40-45 years since we met first in Pune. And yeah, just one point that you agree with me that we have come a long way in proving the twin primes conjecture. Although, of course, it is yet to be proven one way or the other. When do you think, or in how many years is likely to be in one way or the other? Are we still very far away?
It's a very interesting question because I had also been wondering about this. Yeah, I mentioned to when Arjuna was asking this question that yes, one of the problems where we have made lots of advances is a deep problem which we cannot explain here. There's lots of things are involved here, and in the recent years, twin prime problem is lot of advances have been made. So the gap is small now. But if you the question of psychology, are you satisfied with the gap being okay, some finite gap, to 45 or 50 or something, or you want that gap of 2 or something like that? So when you do that, it might become difficult. I don't know because people might lose. I mean, just because it's an old problem, it's of course interesting, but they may say, okay, the main thing was to prove a finite gap in some sense. So they are happy with it, and they may not put so much energy into proving that. All of them may not put energy into this, and they may go into other things. So it might take longer. I don't know. It is very difficult to predict. But definitely you are right that there is huge progress in this problem. It is amazing. And you know that the person Zhang, he was for some time, he left his PhD and he went and told, he was working in McDonald's or something like that.
Yes,
and came back.
yes. That too, he was working in some college or somewhere. Yeah, it was a great work indeed by Zhang, right? Yep. Right.
Right. So it's difficult to predict when.
Yeah,
I
right.
think you here you can ask him what he thinks.
Okay.
But he might have.
See you sometime, Sury. Thanks.
Thanks.
Thanks for the wonderful talk. Thank you.
Yeah, thank you very much, sir, for being with us.
Thank
Actually,
you.
our program has made a chance to meet old friends in this platform.
Thanks.
It's a great initiative. I mean, amazing.
Yeah.
So much enthusiasm is there. I'm very happy to see that somehow, I think it comes from Kerala somehow. I felt this initial initiative. Another Professor Vinod Kumar is there, whom I also know. He runs this magazine called Anantada. Right? So that's also, so I think people are showing a lot of initiative. That's my perspective is, somehow the Kerala people are really doing a lot of it.
Thank you.
Thank you, sir.
Yeah, I have a 1 minute observation regarding some points that Sury mentioned. a couple of years back, there was a survey to choose the best or very exciting result in mathematics. The first prize went to great formula of Euler, e raised to I pi plus 1 is equal to 0. The second prize was shared by two theorems. One, Euclid's theorem on infinitude of primes that Sury mentioned. And second prize was shared by the other formula of Euler, b minus e plus f is equal to 2. Okay, so Euler has dominated to a great extent. I used to have my first semester assignment to the juniors was write a survey of works by some great mathematicians. So one student about 20 years back, who is now a very good professor and very good researcher and professor in the university, said that there is no comparison with Euler. I was thinking that Gauss was the greatest, but he proved that Euler was greatest because of his various areas that Euler has contributed. I think there can be one full session on Euler himself.
You would not agree with this because Euler was the most prolific. He contributed many areas, I agree. But a lot of things he did not publish at the time. In many of these theories he came up with, even he proved theorems on group theory and before formally groups were defined, things like that. So Gauss, I would still, and Riemann again. So some people consider Riemann as above everybody else. It depends on your background.
Okay, so I guess we can move to the final official vote of thanks session. Vinod sir?
Yeah, you may proceed. Yeah.
Thank you, sir. So with this happy note, I would like to welcome Ms. Unnati Shukla, MTech student, IIT ISM Dhanbad, for delivering a graceful vote of thanks for our event.
Okay.
You're audible.
So first and foremost, happy Independence Day to all of you. And thank you everyone for being a part of this webinar. My name is Unnati Shukla and I'm active contributor and teacher in Maths Aspirants. It is such an honor for me to get this opportunity to thank all the dignitaries, contributors, and participants in today's event. First of all, I would like to thank Professor B. Sury sir to take out time from his busy schedule and grace the event. So you talked about the idea of proofs of sum of series 1 by n square, the number of primes are infinite, square type problem, 4-color problem, monstrous moonshine, etc. There are many new concepts and ideas that you introduced us to. It has encouraged me to know more about this wonderful subject, maths. Ms. Arjuna, our host, who has managed to maintain the curiosity and enthusiasm from start to end. I would also like to thank Dr. Bijumon Kumar sir, Emeritus Professor CUSET Kerala, for introducing our speaker. Also, I'd like to extend my gratitude to Ms. Ambyambiki, a degree student in St. Teresa's College, Ernakulam, for designing the promotional poster. And Bijumon sir, Associate Professor, TMG College, Iritty, Kerala, for continuous technical support to the community. And finally, my heartfelt gratitude to the founder of this great community, Vinod Kumar sir, Associate Professor at TMG College, Tirur, Kerala, whose initiative has connected all of us together. In the end, my thanks to our active contributors, Ms. Gayatri, MD Fellow, IMSC Chennai, Ms. Gia Rose Johnson, Research Fellow at Madras, Ms. Kajal Sachdeva, Applied Maths Lecturer at GP Jhajjar, Haryana, Ms. Anne-Marie Tony, Research Fellow, CUSET Kerala. Thank you everyone for joining and making this event a huge success. Once again, happy Independence, Jai Hind, Jai Bharat. Thank you so much.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल अचल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाधा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे